Now we'll next need to learn is connected matrix space. So whenever the things is connected is coming to the mind, that means there has to be a no partition in there, or I can say there is a no separation in there. So for that we need to define what should be the definition of a separation of, when I can say a two sets or one single set has a separation. One set is called having a separation. That means there will be a two portion of the things is there, then we can say it is a separation of between these two. So what the first definition to learn about the connected matrix space, will say it is a separation. What should be the definition of a separation? Let x comma d be a matrix space and A be a subset of X. A pair of subsets A1 and A2 of A are said to be separation of A if it is satisfies the three conditions. The first one, A1, A2, they are non-empty, plus A is the union of A1 and A2. So A1 and A2 will be non-empty. So if we can make them together, then it will create whole space A. The second one, A1 intersection A2 has to be non-empty. That means intersection of both this set is empty. And the third condition is that A1 closure intersection A2 is empty and A1 intersection with A2 closure is empty. Where here A1 A bar represent a closure of A. That means it is A union its limit points. So if you want to say that any set which having a separation, then it has to be satisfying these three conditions. That means there exist two sets whose union is the set itself, and both that set has to be non-empty. The intersection is empty, and the intersection with any of this closure will be also empty. So let's have the example about the separation. So if I consider this A, which is close interval 0 to -1. So as per the figure, we can see that if this is your close interval 0 to 2, and I am removing the point 1 from it, so this point 1, it is not in this set, then definitely this set having the separation or not, that we can say or not. So for that I need to check. So I need to find out two subsets. So let us define this set. A1 will be open interval 0 to 1, which is a subset of A. A2 is 1 to 2, which is also a subset of A. Now we first note that this A1 is non-empty, A2 is non-empty. And A is nothing but the A1 union A2. That also we can say. The second one is A1 intersection A2 is empty. So the intersection of both of this is empty. And the third one is A1 closure intersection with A2. A1 closure, we know that is a closed interval 0, 1. Intersection with open interval 1, 2, which is pi. And A1 intersection A2 closure will also having empty set. So it satisfies all the three conditions. And now you can just see why this condition is added to make a separation. Because if I not consider this third statement, then you can see that we cannot go from this any of this point to this point via path. So that is another way to looking at it is called the path connected in the terms of if you come to the topology or any other definition. So it is called the path connected set. So there will be no path between these two sets, which is A1 and A2. So I can say that therefore A1 and A2 are separates, or they are separated sets. Or I can say this A has a separation, which is A1 and A2. For example, if I have the set A, which is closed interval 0, 2, and this set does not have the separation. That so that means if I want to say that something does not have a separation, that means I have to prove that there will be no any other subsets of this will separate this set, and that is difficult to show because I have to looking at the each and every subsets of that. It does not mean that if I have one set, for example 0, 1 and 0, 1, 2, if this is the two sets if I define, if these are the not separation, it does not mean that any other subsets of this one will not have a separation. So it does not mean that. Okay. So I have to looking at all the pairs, all the possible pairs of subsets. So for that, we have to looking at some another properties of this separation. And ultimately, when we are saying that it is having no separation, that means that is the definition of the connected set. So what is the definition of a connected set? It says that let X comma D be a metric space and A is a subset of X. If A is called connected, then A has no separation. If A has a separation, then A is called disconnected. So that is the definition of the connected set and the disconnected set. For example, the any singleton set X, it is easy to prove that has no separation. So I can say that for any X in X, if X is a metric space, singleton set is connected. Also, we should note that the every metric space X contains a non-empty connected set. Connected subsets. So if you consider any non-empty set, then it always have the connected subset. Due to this, singleton set is connected. The other note we can write that empty set is always a connected set. Empty set is connected by its definition, because it's by the definition it says that it has no separation. So you cannot find out the separation means it satisfies these three conditions. So it should not have any subsets of A1 and A2 such that it satisfies this three property, and that we have, because whenever you have an empty set, there should not be any subset which are non-empty, and therefore these conditions are not satisfied. So that by definition we can say that the singleton set is connected but empty set is disconnected. Now, if you can have any finite set, then a finite set is not connected. So that is the next note I can write. Any finite set containing more than one point is disconnected. That is easily seen. Suppose that is the set x1, x2 up to xn, then you can define a set A1 is x1 and A2 you can put it all other x2 up to xn. And then you verify that all the three conditions for this A1 and A2, which is easy to check. So I can give you this as an exercise to do it yourself. Prove this statement that every finite set containing more than one point is disconnected. Now, the next result is very interesting regarding this connected set. Is says that the set itself, if A, comma D is regarded as a matrix space itself, by itself, is connected. So if this set is connected, then prove that the set which are open and closed in A comma D are only two, which is phi and A itself. So prove that the only set which are both open and closed in A comma D are A itself and phi. We know that in any matrix space X, a phi and the entire set X is open as well as closed. But what is this statement says? This statement says that if you have a set which is connected set, then there are only two subsets which are open and closed both, and they are a set itself and the empty set, which is both closed and open. There is no other set is open and closed both. Okay, so this is very interesting result, and from this result we can easily prove that this we have talked that closed interval 0 to 2 is both open, so it will be a connected set. That we can prove using this statement. That also we can discuss later on. But here this is very interesting result, and it is the main result on the connected set. So let us try to prove this statement. So let A comma D be a connected set. That is the given condition. If the set is connected and A and phi, we have to prove that there are only two sets which are open and closed both. So let us assume that there is another set which is both open and closed. So if A and phi are not the only sets which are both open and closed in A. Okay. So that means there exists some proper subset of A which is both open and closed. Therefore, this is we have assumed. So therefore, suppose that A1 is a non-empty proper subset of A such that A1 is both open and closed. So if A1 is open, we'll define A2, which is A minus A1. Since A1 is open, this is closed. So we note that this A2 is closed because it is open, and since it is a closed, its complement will be open. So this A2 is closed and open both. So if A1 is closed and open, then its complement will be closed and open. Okay. Now we will show that this A1 and A2 makes a separation of A. Since A1 is non-empty and it is a proper subset, A2 is also non-empty and it is a proper subset. So we also note that this A1 is non-empty, A2 is non-empty. Since A1 is non-empty, A2 is also non-empty. A is the union of A1 and A2. That also we can say, because A1 and A1 is there, A2 is the complement of A. And A1 intersection A2 is also empty because they are A1 and A2 are the complement of each other in A. That's why A1 intersection A2 is non-empty. Now what will be the closure of A1 bar? Now A1, the closure of A1, which is A itself, because A1 is a closed. So this is A1 intersection A2 is this is phi, and same argument can be given for A1 intersection A2 closure, that is A1 intersection A2, which is phi. So ultimately what we can say, this A1 and A2 which we have defined here, it's satisfying all the condition of separation. There are three conditions. The first one is these two are non-empty and the union will be make A. Intersection is non-empty and having these two conditions, which is the intersection is phi. So that means what we can say, A1 and A2 forms a separation of A, but which is a contradiction with A is connected. A connected means there is no separation, which is a contradiction. with A is connected. Why we got this contradiction? Because we have assumed that there will be a one set which is both open and closed. So therefore we can say that A and phi are the only sets which are both open and closed in connected set A. So inside the connected set, only open sets and closed sets are only two, which are A, that means set itself, and the empty set. Now with the help of this result, we can able to prove the next result, and which is very convenient to use. So prove that the following statement are equivalent. The first one, that X is connected. The second statement, X is a union of two non-empty disjoint open sets. And third statement, it says that X is union of two non-empty disjoint closed sets. So ultimately, if X is connected, sorry, it is disconnected. So I should write here it is disconnected. So if X is disconnected, then X is the union of non-empty disjoint open subsets. That means X can be written as G1 union G2, where G1 intersection G2 is empty and G1 and G2 are open. This is the way is the meaning of this statement. There exists some G1 and G2 which satisfying this if it is disconnected. This is saying that this X is the union of F1 union F2, where F1 and F2 are closed and their intersection is empty. Okay, so this is the meaning of this statement. We'll prove this result. So I will prove that 1 is in double implies 2, and I will give you as an exercise that 1 is double implies 3 as a homework. The proof is, one can say, similar. So that's why I'm giving you that 1 double implies 3 is as a homework. So let us give the proof of this. So first we'll do this side. Suppose that X is disconnected. Now we use the previous result very heavily here, because previous result says that if X is connected, then there are only two subsets of X which is both open and closed. So what will be the negation of that statement? So the negation says that if it is disconnected, then there will be some open set which is both closed and open. So therefore we can say that there exists a non-empty proper subset A of X, which is both open and closed in X. This is due to the above result or previous result. So therefore, what we can have is X minus A is also both open and closed. Because the complement of a set is a closed and open. So now we define this. X A union X minus A. So what we have to prove, as 1 is double implies 2, that X is a union of two non-empty disjoint open subsets of X. So this A and A complement, both of them are open sets and they are disjoint subsets of X. So therefore we can say that A and X minus A are disjoint, non-empty, open subsets of X such that X is equal to A union X minus A. So that means we can say that X is represented as a union of disjoint non-empty open subsets of X. So that is the proof, the second statement. Now conversely, suppose that X is A union B with A intersection B is empty because they are disjoint subsets, and A is non-empty and B is non-empty. And A and B are open in X. So this is our assumption. That means X can be represented as open subsets of disjoint union of disjoint open subsets of X. Now we have to prove that X is disconnected. So to prove that X is disconnected, we have to show that it has a separation. So hence, what we can define a set, or what we can have here is A, which is X minus B. That is easily seen, is closed because B is open. Since B is open and they are disjoint, A will be X minus B. So A is closed. So that means we can have the A, which is an open set, as well as it is a closed set. A is non-empty, proper subset of X, which is both open and closed. And therefore, by previous result, that X is disconnected. Now the converse part for the other thing, that means 1 is double implies 3, that you can prove by yourself. And this theorem is also can be write as equivalently. If I want to replace this X is in place of connected, then we can write X cannot be represented as or expressed as a union of two non-empty disjoint open sets, and other statement is this. So let us write that is also as a one of the statement. That can be also, you can have a note on that. So let us take it that is as a theorem. So the following statements are equivalent. The first one, the first one is X is connected. The second one, X cannot be expressed as the union of two non-empty disjoint open sets. Third one, X cannot be expressed as the union of two non-empty disjoint closed set. So this is the equivalent statement that we can say by writing the negation. Let us talk some examples based on this. So if I have the metric space X R minus 0 with usual metric, can you say this is connected or disconnected? What is your answer?
Disconnected.
Disconnected. Can you give me a separation of that? That is minus infinity to 0 union 0 to infinity. So this both of them are open subsets of this set. As per this said theorem, it is disconnected, then it can be expressed a union of non-empty disjoint open sets. So these are both of them are open set, and it is expressed as union of disjoint same way. What you can say about Q? Is this Q, which is a set of all rational numbers, is connected or disconnected? It is disconnected due to this. If I define a set x belongs to Q such that x is less than root 2, and if I define another set x belongs to Q such that x is greater than root 2. So one of them is less than root 2, another one is greater than root 2. So I'm separating out here, suppose root 2, all the rational points on this side and all the rational points on this side. And then we can just see that both of them are open sets that you can prove easily. And X is a union of both this, and A and B are open. A and B is non-empty. So therefore X is disconnected. We have two theorems on this that I'm giving you. If some of them is ready to prove in the project, that R is connected. Prove that R is connected. Why R is connected? That I can give you as a homework. Or I can say as a project. If some of them is ready to take it as a project, you can prove that R is connected. The another statement is a subset of R is connected if and only if it is an interval, whether it is a finite interval or infinite interval. Finite interval, sorry, I have written both finite. Finite interval means this AB, if I can write AB, then A is finite, B is finite. That is meant by finite interval. And if any of them is infinite, then it is infinite interval. So whether it is finite interval or infinite, if it is connected, then it has to be an interval. Ultimately, the concept is this, that any subsets of R is connected, then it will be an interval. Now, the very interesting question one can ask here, that if you have a function f, which is from x to y, x and y are both of them are metric space, f is a continuous function, and your x is connected. Can we say that y is also connected? That means under the continuous function, is the connectedness preserved? Like a completeness will not be preserved, Cauchy sequence will not be preserved, conversion sequence is preserved, connectedness is preserved. Like the same question I can ask you about the connected set. The question answer is yes, the connected set is also preserved. Let us try to prove that statement. Or let us write the first statement. What is that statement is? So let f be a continuous function from a metric space x into metric space y if x is connected, then prove that f of x is connected. Now let us have the proof. Let A will be a f of x, which is a range of the function f. We have to prove that this A is connected. So we shall show that A is connected. Suppose not. Suppose that it is not connected. Not connected means it is disconnected. That means there has to be a separation. Or that means as per the result which we have discussed, there exists some subsets of A which is both open and closed. So therefore, there exists a subset B of A such that B is open and closed in A. F is continuous from x to y. Okay, so this is open. So inverse image of open set. So you have something is open in this set y. So therefore I can say that since f is continuous from x to y, f inverse of b is both open and closed in x, which is a contradiction with x is connected, which is contradiction with X is connected. And therefore, this A, which is your f of X, is connected. So this completes the proof of this theorem, which tells you that the image of a connected set is connected. Okay, if you have any question, you can ask.